Now let's see how to derive an expression for the electric field intensity due to an infinitely long straight uniformly charged wire using Gauss theorem. Okay. So first is electric field intensity is as same as the electric field. Okay. And we have to understand what is Gauss theorem. Gauss theorem is the total electrical flux through a closed surface enclosing a charge is equal to 1 by epsilon times the magnitude of the charge, and here epsilon is the permittivity of the free space. This is the equation of Gauss theorem. Okay, they have told that we had taking a long straight uniformly charged wire, and using this we have to obtain an equation for a electric field intensity. But the condition in Gauss theorem is there are two conditions. First, a surface must be closed and charges must be enclosed within that surface. Okay, so we are considering a Gaussian surface. The surface which we consider for the Gauss's theorem we called as Gaussian surface. Okay, so here Gaussian surface is cylinder. First of all, to calculate the magnitude of electric field, we imagine a cylindrical Gaussian surface. And next, we'll consider a point on the curved surface of the cylinder, which is P, and distance of that point from the wire is R. And next is the electric field at that point is just normal and outward. Okay. And next also the area vector. Area vector is ds. Area vector is also along the outward normal to the curved surface and are in the same direction. We'll start with our derivation now. The first one what we have taken is to calculate the magnitude of the electric field. We have considered cylinder. Okay. Of electric field, consider cylindrical surface as Gaussian surface. Okay, and the next one is to calculate the magnitude of electric field at every point. See, at every point on the curved surface the magnitude will not change, because if we consider any one point on that such surface, the distance of that point from the wire is the same. Right. So the magnitude of electric field, E. Okay, E at every point on the curved surface. Point on the curved surface remains the same. Surface remains the same. So this is because remains the same. This is because all the points are of same length or distance from the line charge. Next one is the electric field and the area vector are in the same direction. That is, they are outward and normal to the curved surface and they are in the same direction. So the theta angle between these two is 0 degree. Now is electric flux. We are coming to equations now. Electric flux over the curved surface. Here we have to calculate electric flux on two surfaces, over the curved surface, over the edges. Okay, electric flux over the curved surface, that is phi 1 will take. Phi 1 is equal to E dot ds is the equation. Phi is equal to E dot ds. Here we are considering summation E dot ds. Okay, the total flux we are considering. Okay, flux over the curved surface only, not over the edges. Okay, E dot ds, and here E will take common. E is a constant, so it will come out. E is an electric field. It remains the same, and ds. ds is the area of that surface. Area of the curved surface. Area of curved surface of cylinder. Surface of cylinder is 2 pi RL. So phi 1 will get as E2 pi RL. We'll consider this as equation 1. And next we are done with the curved surface. Now we have to go to the edges. On the ends of the cylinder, the ds, the area vector is just outward and normal, right? Outward and normal at that point. If we see electric field remains the same. Okay, electric field is in this direction, but ds is in the downward direction. If we see the angle between the E and ds on the ends, if we see the angle between E and DS, the angle between them is equal to 90 degree. Therefore, they do not contribute to the electric flux. Contribute to electric flux of whole cylinder. Electric flux of the whole cylinder. So, the total electric flux will only be E into 2 pi RL. Okay. And therefore, the total electric flux over the cylinder. Okay. Electric flux over the whole cylinder. That is phi is equal to E2 pi RL. Okay. This is the equation next. And next one we have to see what is linear charge density. Linear charge density formula is lambda is equal to Q by L. And Q is equal to lambda into L. Okay, this is the third equation. Next one is Gauss theorem. The formula I have already told. Phi is equal to Q by epsilon naught. Here we got phi value. Phi is equal to E2 pi RL and Q value is lambda into L. We will substitute these two values in this equation. E2 pi RL is equal to lambda into L by epsilon naught. What we are going to calculate? We are going to calculate the magnitude of electric field or electric field intensity, right? This is the electric field intensity or electric field representation. So, we need the equation for E. Here L will get cancelled. So, E is equal to lambda by 2 pi R goes on the other side. It will be in denominator 2 pi R epsilon naught. In vector form, we can write as E bar is equal to lambda by 2 pi R epsilon naught n cap. And here n cap is the unit vector or the radial unit vector. Okay, radial unit vector in the plane, which is normal to the wire. Normal to the wire passing through the point. And this one we have to mention it for sure through the point. Okay, thank you.